Hello. Are we live? I think it's working. Okay, so today we are going to have a look at a bit of a library that I'm building. It's not, at least at the moment, anything practical. I just saw some interesting algorithms and I thought, hey, it would be fun to do that, and why don't I try implementing those in Rust? So I was looking at Reducible, which is a great channel. If you don't know it, if you haven't heard of it, it's a bit like 3 Blue 1 Brown, but more specifically for computer science. Obviously, he has done neural networks and stuff. So he's done lots of really interesting algorithms. I'd love to look at some of the graph stuff and the Fourier transforms. It's all really interesting. But one thing that I thought was particularly interesting was the Huffman codes and then the compression, the various compression algorithms. And I think, for example, and in the PNG one, he talks about QOI, which is, you can watch the video, he explains more about it in depth. But it's a much simpler and much faster version, implement the compression algorithm based on many of the same ideas of PNG. So loss, I can't remember whether it's lossy or lossless. Anyway, but it uses discrete cosine transforms, I think, and other methods, basically to discard very high frequency data that's a lot less visible. He also talks about other things like chroma subsampling. But I thought lots of the ideas were really interesting, and I particularly thought that the Huffman codes were interesting. So I wanted to implement these, and Huffman codes is one of the easiest places to start. So that's what I've been looking at. So you can see here. So I've started with a library building a crate called Compactor, and this is, I've obviously started. I've got Huffman coding working, though it's a bit slow and I'm not entirely sure why. So that might be an interesting thing to try and look at. I haven't I've gone through most of the Rust book, but by no means an expert. I haven't I've coded a couple of toy things, but not much sort of larger projects or anything too serious. So it might be interesting to see how that could be optimized. But my intention with this is, thought it would be interesting to make a command line program that you could use to compress and decompress files. So because I've done the mini grep in the Rust book, but I haven't done any more serious command line applications. So it might be interesting to look at clap or other command line parsing things and dealing with files. But I thought for today it might be probably be good just to go over the code that I've written so far. If anybody knows of anything I can do to improve it or any other ideas, this is just me knowing what Huffman codes are and thinking, well, how would I make that work? And there's quite a lot of things that I know are not great and not very efficient, and I've been thinking about how to do them into files, serializing the trees, and they've got the count, so we'll see that in a minute. But there's definitely a lot of work. So this is the code that I've written so far. I've got this is just not doing anything. So this is the main module. That's just a sort of helper function. So basically, if we look in the tests here, you can see I've got the oh yeah, it doesn't work very well on the in VS Code. When you do the test, it prints out everything, so you can see that this is the encoding of various things. But basically, what it does is I have methods to encode. So this is my function here. So you can encode this text, and then that will give you the encoding, which at the moment I'm modeling as a vector of enums, which are either left, right, and that describes the path through the tree. And then I've got this here, which is the actual tree, and then it should then we'll print those out if there's an error, and then you get and then it just decodes them, just passes them both, and then they should be equal. So that mostly works. So what I'll do for today is just go through the code. So the way that I've done the tree is I've done it using nodes. So it seems like a slightly convoluted way to do it. There might be an easier way, but when you encode, when you build a tree for Huffman encoding, as far as I know, each node will always have either a value or two connections. So I've got a node here which has a frequency which we use for building the tree, and then it has a value, and I can set that value. That value is an enum, which is either a char. Now I might transition. I've been thinking about moving the chars to U8 because there's no reason why it shouldn't work on bytes in general, but as far as I know, chars and U8s are basically the same thing in terms of the way they operate. It's just how the compiler interprets them and how they get printed and that kind of thing. So that should be a relatively simple fix if we want to do that. And then obviously at some point it would be nice to make it more generic. So it could be over some type T. Probably have to be a stack value, but I can get into that another point. And so this value of each node is either a character or this connection struct, which just has a left and a right, which are then box pointers to other nodes to keep the borrow checker happy. So what happens if we go back up to the encode? It takes the text, which is the input, and I've got this string to token frequency method, and what this does is it goes through, it iterates over each of the characters, and it makes a hash map. If there's a new one, it inserts that character with the value of 1. Otherwise, it increments the value that is there. And then it takes, so at that point, there's a hash map of keys, which in this case are characters, and each of them has a frequency of what they appear. But that's not very helpful for building the tree. So what I do is we we iterate over those keys and values in it, and then for each of those, we create a new node with the frequency of that frequency that we've already calculated, and then that token as its value, and using this huff value enum. So basically at that point what we've done is we've created all the terminal nodes or leafs, all the ones that are at the end, and then what we do in the next step is we connect them together and then we build them up into the tree. So all of the nodes that we add at this point are just going to be basically connecting other nodes. So all of the ones that actually have the values are done at this point. But when we've got that, when we've done to token frequency, so we've got that vector, we then do the list to tree. So this does that. This just checks because if you have an empty string, it doesn't like you very much. So this just puts in a 0, basically a null byte, which doesn't do anything, and it can actually be anything. It's entirely arbitrary because it will never get to it. The nice thing about this is that you could actually inject as many characters as you want. It's just, and as this has 0 frequency, it wouldn't make any difference. Shouldn't, I don't think. But it might reduce your efficiency, but because as long as you don't have any paths getting to them, it wouldn't affect it. So, and then what we do is we loop over them and we sort them. This is just a pretty simple thing which sorts them on the frequency. So the way that Huffman works is that you take all of your nodes and you sort them by frequency. So you have the highest frequency at the top and the lowest frequency at the bottom. And then you take the 2 lowest frequency nodes and you combine them together into a new node which has connections to each of those. And then you add the frequencies together, that's the frequency of the new ones. And then you just iterate until you just have one root node with all of these other connections. And that gives you the most optimal encoding for text on a character by character basis. There are other ways you can do it. You can use larger chunks of data, but that gets into other issues. But for actual text, this is the most efficient way you could do it. Anyway, if you can watch the reducible video, there are quite a few good videos on it, I think. If you're interested in more of the details, but I always find it funny because it was set as homework. I can't remember what university he was at, but it was set to him as homework, as an assignment by a professor, his whole class. But what he didn't tell them is it wasn't solved. They were set a problem which is to find the most efficient algorithm and one that's guaranteed to always give the most efficient encoding. And the current, at that point, the one that was the best was one that Shannon worked on, because of course it was. But it wasn't perfect in all cases. It usually, my understanding is, it usually gave the optimal solution, but it didn't always. So, and he figured it out. So anyway, so what this does is it sorts the nodes, and then it pops the last 2 nodes off of the stack, off of the vector rather. And so those are because we sort it in descending order, those are the 2 nodes with the lowest frequency. And then what we do is this Huff nodes has a from nodes associated function, and so that just builds a new node with connections to those 2 nodes that we've given, and then we just put that back on the end, and then we just repeat that until we only have 1 left, and then we pop that off because there's only 1, and then we return that, and so then that's our tree. And then encode, and then we got the tree to code. So this is this is the way that I've done taking the tree and turning it into actual codes that you can then, because encoding in Huffman is easy because you just look at the character and then you can just look up what the code is. It gets a bit more complicated in the decoding. That was quite tricky because each each character has variable bit length. So instead of just saying, let me look at these 8 bits, what does this mean? And then that's what it is. You have to be more subtle about it because an E, for example, or something else that's very common might only be 2 or 3 bits, but your least common letter might be 10 or 12. I don't know, it depends on what you've got, but there'll be quite a wide range, which is why it's better, because the things that appear very frequently you're only allocating a very small number of bits to, and the ones that occur frequently, well, it doesn't really matter. We can afford to use lots of bits to encode those because we don't have to do it very often. So what this basically does is it looks. I've done this recursively. That it looks at the root of the tree, and it looks at a node, some subsection of the tree, and it says, is this a character? If it is, then that's fine. I don't have anything else to do. I'm all good. But if it's not, then that node will have connection to 2 other nodes, and it says, well, hey, I want to solve this. I want to basically find the codes for everything that's in those branches as well. So if it's a character, it inserts that token and the path onto this accumulator, which then gets returned. So basically what I've done is, if you see here, it gets called with an empty vector, which I find slightly clunky. One of the things I wish Rust had, and I know it probably causes problems, but I wish it had default arguments, because then I wouldn't, or optional arguments. Obviously, you can have arguments that are options, but you still have to put something in them, which I find annoying. From what I remember reading, I don't think there's much of an intention to implement that, but it would make this kind of thing more elegant, at least to me, if I could just say that it equals that. Anyway, it probably might cause some problem, I'm not sure. But basically, we take this path, which is the instructions to get to the node that we are now. So that's when we call the function initially. When we call the function initially, we're at the root. There's no instructions. That's just where we end up. But for each subsequent one, there'll be some combination of left and right. And the path, I've just made an enum, which is just left and right. One of the other things that I've been thinking about and not exactly sure how to do is how to write this into a file in binary, because I haven't been able to find a way to write a 1 or a 0, because everything seems to be in bytes. So that might be an interesting. I've got a couple of ideas of how I might be able to make a struct to do that has a byte array and then a pointer that allows you to push a 1 or a 0 to it. So basically a binary buffer or vector or something like that. But it'd be more like a stack, but not sure about that for now. But basically, so it has a path, which is a vector, the instructions of how to get where it currently is. And if it's on a token, then it knows that that path is associated with that character. And so if we see that character, use this path and you'll be able to get to it. So we just insert that into this accumulator, which then gets returned at the end. But if it's not, so if we have connections to other nodes, this is where the advantages of Huffman is, because the let me see if I can because each node either has connections to two other nodes or a value. You don't have to worry about the case where you have a value and a connection or some other combination. You've either got a value or connections. So what we can do is we can call the connection, we can call this function, this tree to code function, on that subset of the tree. So the way that we do that is that we take the left node here, which is not the most elegant thing here, but because this is a box pointer, we want to dereference it, and then this takes a reference to it. So that's why we have to do the reference of the dereference. And then so we take the left one and the right one, and for the left one we tell it to do that with the path that we've got at the moment, but with left added onto it because we're doing the left one, and we do the basically the same thing for the right. Let me just, so what we're going to the tree will always look something like this. So what we can do is we can call the function here with an empty path, and then this will call the function again on each of these two nodes here. And when it calls it on this one, it will be with the path of right, and it says, I don't know if this is an E or something, then it would say, I know that E is associated with right, and then it's going to send that back up to here. And when we call the function here, we've got left, and it says, I'm going to call the function again here. I don't know if this is B or whatever. This looks, and now this is left. So now this knows that B is associated with left. And so it sends it back up to here, which will collect all of these ones. Which these ones will send it back up to here, this will send it back up to here, and then this node will send them back up to the root node, and then that will return from the function. And then we'll have a full list of each of our encodings. So that's what this tree to code is doing, and so what that will return is a hash map. And so that means every character that we want to encode is really easy. It's just to look up in a hash map, which I don't know what the time complexity of that is, but it's not very much. Because hash maps are pretty fast. There might be a way to optimize that more, but I think that's how it works at the moment. And then all it does is it takes our it takes the text that we've got, and it iterates over the characters, and we run a map, and that just takes the character that we've got at the moment, and it looks it up in our hash map, and then it clones that because we need to return something that's owned, and then it flattens it. I think the reason for that is that it came out as a vector of vectors, I think. I can't remember exactly why, but because each of the paths comes out as a vector. So if we have A, B, C, D, let's say, each of these will have some encoding. That they'll be transformed to, and these will all be in a vector, but we want to output something that just looks like this and has all of the things in here. And then at the other end, we need to have the tree, and then we need to figure out, we need to add these, when we're decoding it, we basically need to add these back in, and we need to figure out where one character ends and the other begins. So we flatten them, collect them into a vector, and then we return the tree so we can then decode it. Now I'm thinking about different ways that we might be able to optimize this and be able to do it to send the tree, because obviously, well, at the moment, the tree always has the frequency. So each node always has a frequency, which is not what we really want necessarily if you're storing it or sending it. That might be true, but you'd want to be able to operate on a tree that doesn't do that. So I was thinking that instead of having left and right as properties, we might be able might implement it as a trait. So that would be a standard set of methods, and then the frequency one would be an optional one, or if it didn't store frequency, it would just panic or return an error or do something like that, so that the decoding, which doesn't use the frequency, wouldn't have to use it, but the encoding could still use it, but they could use a sort of one type or have one trait that could either have frequency or not, depending. But anyway, so that's how the encode works. And then the decode just takes the output of that. It takes the encoding, which is the vector of the paths, which is just that left, right, enum, and a reference to a tree. Just set up an accumulator, and then we do the vector. Now this was with a I think, if I remember correctly, it was a little while ago, but I think that's basically a queue implementation. So what we want to do is we want to look at all of the instructions that we've got so far, and we want to go through each of them, and we want to look at the node that is there until we find one that contains a character, and then we return that character back up, and then we keep going. We're starting again from the top. So we're looping over them. Suppose we could probably do a while loop. But, anyway, so basically, while there's things left in it, we want to push onto our accumulator string the next character, which is what this traverse tree function does. Is it just basically finds the next character. So it takes the tree, and it takes a mutable reference to the remaining, and so it's actually going to pop or DQ, I can't remember what it's called, but it's going to take values off the front, and so that's a global mutable thing. And then in the end, we just return that which should have the whole string. So in this traverse tree function, we look at the path that we're currently at and the tree, and we look at the value of the node that we're on, and if that is character, then we just return that. It's that simple. But if it's a connection, then we do sort of a similar thing that we did when we were encoding it, when we were trying to find that coding system, we look at we pop the front off of the queue. So that's looking at the next instruction, and we go to that node. So if it's left, we go left. If it's right, we go right. So basically, we're going to keep calling these functions at each node, and if we have so let's say, I don't know, we're going to, if we've got right, left, right, we call the function here with right, left, right, and then we pop the front one off, and we do what it says. So then we call the function again on this node, but this time just with left, right, and then we do the same thing again. We call this one with just right, and then we call this one with nothing. Well, actually, with either nothing or whatever the rest of the encoding was, but it doesn't matter because it looks at this. This is going to be a character, it's a terminal node, and then it returns that one, but it's removed the instructions from the queue that are associated with that token. So we do that, and then we just loop over those until all of them are done, and then we print out the string. So you can see the intermediate stuff. So what we can, just as some examples, let me just copy this stuff so we can happy with me now? That's fine. So then we can just there we go. That's nice. So if we can see here, this is, I'll just do something, I'll just do AAB, because that should be easy. So we can see here that initially, our initial nodes are, we have one which has a value of token A and a frequency of 2. There are 2 A's, so that checks out. And we have one with value B and frequency 1. Again, that's fine. So now we can see here that, and another thing that would be interesting to look into is a better way to print them out, because when you start having larger trees, it gets very confusing. But we have one with value which has connections, and the left one is A with frequency 2, and the right one. So we have the root node, and it has here to A, and then there to B. It's basically what it is. It's not doing any of the joining. If we do A, B, C, then we get a slightly more interesting structure here. We've got what we'd expect there. But this time, our left on the root node here, which is this one here. Oh, sorry. This one is the root node. The left one has a value of A. And then the right one is a node which has B and C. So basically what this one looks like is it has A here, then it has another node with B and C. So you see how this A1 which occurs most frequently, it occurs half of the time, has half of the information of the other ones. And obviously those trees get bigger and more complicated as you advance. So then it does the encoding. So left, left, left. We know each of those A's. Right, left, that's a B, and right, right is a C. So that checks out. That's I should just call that tree. Anyway, it doesn't really matter. So we can see here's the key, and then when it's decoding it, you can see this is the initial. This is the initial path, or the sequence, the encoding, and you can see each time it takes the next one off. So it pops the left off the front, and then that's an A, and then it goes again, pops it again, A, but then you can see here it pops it twice before it does the B, because that B is associated with 2 instructions. It goes all the way down till it's empty, and then it returns that. So I hope that has been interesting. That's an overview of what I've done so far. If there's anything egregiously wrong, let me know. I've done some tests with some longer files and it is a bit slow. I'm not exactly sure where that is. Haven't done a huge amount of sort of practice with that kind of thing, but it would be nice to be able to do that. And I know it shouldn't be taking that long. I was doing some random tests and it was taking absolutely forever. So that would be a good thing to look at. It certainly be interesting, and then turning it into a command line tool, and being able to parse files and things like that, and then eventually going on to some more complicated algorithms be interesting to look at, but ultimately being able to do QoI, possibly starting with simpler, but image, audio, compression, and that kind of thing would certainly, I think, would be very interesting. So if you'd be interested in that as well, please like and subscribe, and hopefully join me on the next video. I do plan to continue with the other with my other projects. Configurematic was one that I started a video on a while ago. I would like to continue with that. And I've got other things. For example, I'm inspired by neural networks from scratch, the CentDex series. That's in Python. I've been working on an implementation again in Rust called Didact. You can see some lovely errors here, but basically working through it. And I've basically got a network type and layer types, and traits rather, and then those, and so you can build up, you should be able to build up layers in a network, and then call forward. I've got forward propagation working, going to be looking at and actually train that soon. So if any of that stuff interests you, I hope you'll stick around, and I'll see you in the next one.